The next problem we want to discuss is called fractional knapsack. If you want to be correct, you can call it the fractional knapsack problem. Well, imagine that you are a burglar. Okay, I'd always wanted to start an algorithms lecture this way. So here goes. So imagine you are a burglar, let's say successful one at it. So you have so you set out to burgle a house, and you have a bag with you, or a knapsack. Okay, that's where the word knapsack comes from. So you have a sack with you, and you enter the house. Well, you are a pro at it, so you enter the house. Then you find that you have really hit the jackpot, in the sense that the house has all kinds of stuff in it. But you see, your sack, has limited capacity. You cannot just take everything away which is there in the house. Okay. So the crucial question that you have to answer at this point is, what do you stuff into your knapsack? What do you stuff into your bag? Now each item has a size, right, and there is some profit associated with it. So if you sell it, there is some cost or profit that some money that you get out of it. Okay, so each item has a profit and a size. Now the total amount of items that you can take back with you is restricted by the size of your sack. Okay, your objective is to fill this sack with items such that the total profit is maximized. Okay, so you would like to somehow decide which items to put into the sack so that the profit is maximized. Well, this is the knapsack problem, okay, without the fractional part. Well, if you could take fractions of each item, okay, then it's called the fractional knapsack. In the sense that, imagine that you're not burgling an ordinary house, you're burgling a cake shop. Okay, then there are all kinds of cakes, fancy cakes strewn around, and you can take fractions of each cake and sell it. No, you can't eat it. Okay, so you can't have the cake and eat it too. So you have to sell these cakes. You can take a fraction of each cake, and your job is to sort of choose those which can fit into your bag. You have to make sure not to squish them. Okay, and you want to again maximize profit. So this is the fractional knapsack problem. So let's get back to our real vocation, which is designing algorithms, and let me define this problem formally. Okay, so there are n items. Okay, each item has a profit and a size associated with it. Okay, so this is Pi and this is Si. Okay, let's say 1 less than equal to I less than equal to n. Okay, each item has a profit Pi and a size Si associated with it. You have a knapsack of capacity B, say. Okay, this is input. So this is the input, which is each item has some profit and size and a knapsack of capacity B, and the output is for each item you have to say what fraction of this item you're going to take. Okay, so you are given each item, there's only one unit of an item which is available to you. You have to take a fraction of this item. For each item you have to say what fraction, so that the total size is at most B. You cannot take more than what the knapsack can contain, and you want to maximize the profit. Okay, so let's again write this down mathematically. Okay, so let me recall, you are given, so you are given P1 through Pn, okay, S1 through Sn. This is these are profits and sizes, and B. This is the capacity of the knapsack, right? Okay, what you want is, so you want to find x1, x2 up to xn. That is what fraction of each item that you want to pick. Okay, so what should these satisfy? Well, you want to maximize the profit. So, for 1 unit of item 1, okay, the profit is P1. For x1 units, it is x1 times P1, right. For instance, if x1 were half, the profit would be P1 by 2. Okay, so you want to maximize sigma xi pi, I going from 1 to n, okay, and the total size of these items that you pick should be at most b. Okay, so this says, so that sigma xi si is less than equal to b, okay, I equals 1 to n. And let me remind you that xi's are fractions, so 0 less than equal to xi less than equal to 1 for all I. Okay. So, mathematically this is the problem you want to solve. The input is P1 through Pn, S1 through Sn, and B. Output is x1, x2 up to xn. You want to maximize this profit function, which is sigma xi pi, and the xi should satisfy these two constraints, which is the first one is this, that the total size is at most b, and the second is they must lie between 0 and 1. So, this is the fractional knapsack problem. Okay, this is the problem that we would like to solve. Okay, so how does one go about doing this? Well, we are still within the realm of greedy algorithms. Okay, so I guess one just has to be greedy and pick as many cakes as one can. Yeah, so what we would like to do is pick these items one by one. Okay, so that's what a greedy approach to this would be. So the output is roughly looks like a subset. It's a fractional subset, not quite a subset in the real terms, but still we would like to do this greedily in the sense that we would like to pick elements one by one. Okay, so we would like to use the greedy approach. Which means pick items one by one. So the crucial question here is, the crucial decision that you want to make is this ordering of items. How do you order items? Okay, to pick. Well, one can come up with all kinds of orderings, right? You can say, so here is one, for instance, decreasing profit. So you could look at items in decreasing profit, according to decreasing profit, and pick them. Well, increasing sizes. Okay, and you could sort of put profits and sizes together into various functions, and let us say profit by size, or profit by size squared, profit squared by size, etc., and you know, you can ask which of these work. You can try all of these. Do these things work? Well, that's one way of sort of approaching this. Try all these, you know, various possibilities that go through your head and which don't go through your head, and you know, try and prove that these possibilities work. Remember that coming up with possibilities is not too difficult, right? We've just listed out many. Coming out with the right kind of order is the crucial, is the sort of key here, right? And so how do we do this? Okay, one is, well, we sort of, one way is to come up with these things and see if you can prove one way or the other. Either come up with examples so that the strategy works or fails, strategy fails, or you try and prove somehow that the strategy works. Okay. What we would like to do is to use this the ill-defined exchange trick that we mentioned, and see if we can use that to design this algorithm. Okay, so that's what we are going to do. So we are going to take this exchange trick somehow, exchange item, basically put one item in, put the and exchange one item for another, and see what happens to the profit. Okay, and that hopefully will guide us as to how to come up with this ordering on elements. Okay, this doesn't always work, but in cases where it works, it works. Okay, so let's try this. So supposing, yeah, so let's write this down. So we would like to use the exchange trick here. So remember, this is just a way to design the algorithm. Okay, this is some kind of trick that you can use. I'm not guaranteeing that this will work always. Okay, it is just a hint that I give you. Okay, so let's try this. So what does the exchange trick look like? We would like to exchange, okay, some portion of item I for item j, say. See, we have two items I and j. I would like to put more of item j in and take out some amount of item I, and then I would like to see what happens to the profit. Of course, I have to make sure that the bag doesn't burst. Okay, so we can assume that we've started out with a solution in mind, and we would you can assume that the bag is full. If it's not full, I can put I can start filling in arbitrarily some items till the bag is full. So we take, let's say, y1 of item 1, y2 of item 2, and so on, yn of item n, such that the bag is full. Okay, and from now, with this in mind, now I'll exchange one item for another, so that the bag still remains full, and then we'll see what happens to the profit. Okay, so that's the sort of calculation that I would like to do. Okay, so we'll assume yt units of item t picked. Okay, and so what's the, we'll also assume that sigma ytst t going from 1 to n, okay, is exactly b. Okay, so the bag is full. Okay, so what's the profit? The profit is nothing but sigma yt pt, right, t going from 1 to n. This is the profit. Okay, now what would I like to do with this is remove some amount of item I and increase some amount of item j. Okay, so in my new thing, okay, initially I had y1, y2, okay, somewhere I had yi, somewhere I had yj, okay, yn. Okay, this is what I have. Now what I would like to do is make this, let's say, yi minus epsilon, okay, for some small epsilon, and this I would like to increase by some amount, let's say yj plus epsilon prime. This is what I would like to do, which is I have replaced some portion of the ith element with some of the jth element. I would like to maintain the bag to be full. Okay, I would want these transactions to be such that the bag is still full. Then I would like to see what happens to the profit. Okay. So, what does it mean that the bag is full? It means S1 Y1 plus S2 Y2 and so on plus Si times Yi minus epsilon plus so on Sj into Yj plus epsilon, okay, plus Sn Yn equals B. Okay. Okay, so this says sigma Si Yi, sorry, St, let's say Yt, okay, T going from 1 to n, right, plus Sj times, okay, this is epsilon prime minus Si times epsilon, okay, equals B. Well, this fellow I know is already B, because initially I started out with the bag being full. So, we have that Sj epsilon prime equals Si epsilon. If I want the bag to be full, then I get that epsilon prime and epsilon I can choose in the ratio of Sj to Si, right. Okay. So, let us see what happens to the profit. So, what happens to the profit? Okay. So, what is the new profit? The old profit we know, the new profit is new is P1 Y1 and so on, okay, plus Pi into Yi minus epsilon, so on, plus Pj into Yj plus epsilon prime, and we go on and on up to Pn times Yn. Okay. So, this is nothing but the old profit, which is P1 Y1 and so on, Pi Yi etc., Pj Yj plus Pn Yn, okay, plus minus Pi times epsilon plus Pj times epsilon prime. Okay, so, the new profit is nothing but the old profit minus this plus that. Good. Okay, so now the profit, there is a profit increase, there is a, so this is what we want. Okay, when is there a profit increase? If well, this fellow is greater than 0, which means Pj times epsilon prime is greater than Pi times epsilon, which means Pj by Pi, okay, is greater than epsilon by epsilon prime. Okay. So, there is a profit increase if this is true. Let me just pull back an old slide. Okay. Now, this says Sj times epsilon prime is Si times epsilon, which means epsilon by epsilon prime is Sj by Si, right. Now, so let us just put this back into that other inequality. We are going to put this equality into the other inequality. Okay, so, this epsilon by epsilon prime is nothing but Sj by Si. So, there is a profit increase if Pj by Pi is greater than Sj by Si, or Pj by Sj is greater than Pi by Si. Okay. There is an increase in profit if Pj by Sj is greater than Pi by Si. Okay. This tells you what to favor. Okay. I remember this happened if I replace part of item I with item j. Okay. I should favor item j if Pj by Sj is greater than Pi by Si. That is what this calculation tells me, and that is what my algorithm will be. Okay. So, you can see how just using this exchange trick we have actually devised an algorithm, and we will in fact also prove that this algorithm is optimal, right. Okay, so the score of an item is nothing but profit divided by size, okay, and the algorithm is simple. You say the algorithm says order items by let us say decreasing scores, okay, and well, pick these items in this order and pick them in this order till you fill the knapsack. This is the algorithm in one sentence, okay. So how will the output look like? Well, you would pick the first item, okay, the one with the top score. You would pick that item, you will pick the next item and so on, and at some point, you know, you would have picked these items, and the next item there may not be enough space in the knapsack. So you don't pick the entire item, you pick a fraction. So the first few items, okay, if I pick k items, k minus 1 items will be, I will pick the entire item unit, okay, and the kth item will be a fraction. So in my solution there will be one fraction which is the last item, and the rest of them will be units, okay. That is what the output looks like, okay. So the algorithm, so if I look at, let us say x1, x2, so on, this is the output, right, and let us say 1 is the item with maximum score. So this is items by decreasing scores, right, this is the maximum score and so on, this is the least scores. Then, and this is the output, is output, then it is of the form, the sequence is, okay, and let us say it is of the form 1 1 1 up to some level, and then some, let us say delta which is between 0 and 1, and then 0 0, okay. This is how the output looks like, okay. We need to now prove that this indeed works, okay, that this algorithm, the output that this algorithm gives you is optimal, okay. So let's prove that this is optimal. Okay, so so we would like to compare this with any optimum and show that this is optimum, okay. That's the way we would like to do it, and we would like to use the exchange trick again, okay, but now to prove that it is indeed correct, okay, and we will use it the same way we used it earlier, okay. So please sort of review that material if you've forgotten. Okay, so the proof goes this way. So supposing, so let Z1, Z2, Zn be an optimal output. Okay, let me recall that our output looks like this. It's x1, x2, xn. It looks like 1 till something, okay. These are in decreasing order of scores, then you have a delta and then zeros, okay. This is how our output looks like. Good. So let Z1, Z2, Zn be an optimum output. Again, the items are, the order of the items are the same, okay, in both. Z1, the item 1 is the item with the top score, okay, but this is the way the optimum picks. If it is of course 1 1 1 and then delta and 0, then you are done, because this exactly equals Z exactly equals x's, right. Now let it's possible that Z1 equals x1, Z2 equals x2, but if they are different, there will be a first index where they differ, okay. There will be a first index where they differ, okay. So this is what, so I am going to what we are going to do is we picked more of this item. In the first index, let us say the ith index, they differ, then here we picked more of I and he picked less of I, okay, because we picked 1 unit of I and he is picked let us say less than 1 unit of I, okay. Then we would like to see what happens if we increase, we take the optimum, increase the ith and we decrease something some other where which has a lower score, okay, we can do this. And using the previous sort of calculation that we did during the exchange trick, we will see that the profit goes up, and this is it, this is the argument, okay. So let us just formalize this. So let j, okay, be the first coordinate okay, where zj is less than xj. Okay, this is also the first coordinate where they differ. Well, I will let you observe or prove that the first coordinate where they differ, zj will be less than xj and it will not be greater than xj. Okay, that is the way we have picked x's. Okay, they are ones till some stage and then there is a delta, total sum is b. If I increase any one of them, okay, it can't be. The ones I cannot increase obviously, and if all the initial things are 1, I cannot increase this delta because then it will be greater than b. Okay. So, the first coordinate where they differ, zj will be less than xj. Okay. So, so then there is some I, okay, which is greater than j, where zj is greater than xj, zi is greater than xi. Okay, there is some xi where this is true. Okay, because the total of both of them is b. Okay, now what I do is I increase the profit. So one can increase the profit here by doing this. So take z1, z2, okay, zj plus epsilon and so on, okay, zi minus epsilon, so on up to zn. So look at this epsilon prime, okay, do the same calculation that we did and you can see that the profit, remember at the end of it we came up with a new profit which was greater than the old profit. Of course, we need to choose epsilon and epsilon prime properly, and I will let you look at, I will let you do this, okay. So go back to this old calculation that we did, figure out what epsilon by epsilon prime should be, right. I again have enough items to fill the knapsack of size b, okay, but the profit has strictly increased, which means that the original z1, z2 up to zn was not optimum. Okay, that is a contradiction. Okay, so this is for a contradiction. And calculate the profit for contradiction. Okay, I must say towards okay, that's the end of the proof. I'll let you sort of frame this better and write it properly. Okay, there is one small thing about this proof which I should say. Supposing so let's say that these items had the same score, they all had different scores, then there is no problem with this proof, it works perfectly. If their scores are the same, then you need to worry about it, okay. You need to modify the proof slightly. Basically I could have chosen, you know, an item with among items with the same score, I can sort of choose any one of them, right, and I may differ from the optimum in this respect, but it's only in this respect. Okay, that part of the proof I'll let you sort of fill in, but modulo that, okay, modulo that, this finishes the proof of correctness of the algorithm to fill up knapsacks. Okay. So again, let me emphasize this that the right the right order that we want is to pick to look at the profit by size. Okay. This is also, you could have come up with this intuitively also. You know, your intuition could have told you. In fact, I mentioned it initially, that you could look at profit by size as a measure which you should follow. But to sort of, the way we got it was just by trying out this exchange idea, and well, we just exchanged two things and we saw what happened, and profit by size came out naturally from this exercise. Okay. So that is the model that I want to convey to you, that often when you are faced with problems of this kind, just do this exchange trick. Okay, run over this exchange trick, see what is the quantity that comes out, and that quantity hopefully will let you dictate what your algorithm should be. The next problem that we look at comes from the area of information transmission, and it's related to codes. Okay, so we would like to design codes which have some properties. Okay, that's the next problem. Okay, so the problem is like this. So you have symbols x1, x2, and so on up to xn. So you have n symbols. Okay, each of them has a frequency f1, f2, fn. So these are symbols that are sent on a channel from, let's say, place A to place B. Okay, these are symbols which are sent from one place to another, and this is the frequency at which they are sent. Okay, and what we would like, so this is the input. So what we would like is codes, C1, C2. We would like to code them, okay, using C1, C2 up to Cn. These are let's say binary codes. Okay, each of these is a binary string, and we would like these binary strings associated with each of these symbols. So for instance, if I send C1, C1, C2, it means you have sent symbols x1, x2, the word x1, x1, x2, right? So to send these symbols, I just send these codes which are sort of decoded at the other end. And what you send is not a symbol at a time, but a huge word at a time. Okay, so you have this huge sort of string which you keep sending from the left, and at the right you sort of pull out those strings and you decode it. So this code is the output. Okay, so if it were not for the frequency, okay, there is nothing much to this. I have n symbols, I just write down, you know, n short strings as codes, and I send them out. The frequencies that make things a bit difficult. Okay, so let's take an example. Okay, so for instance, I have symbols. So here's an example. I have, let's say, A, B, and C, 3 symbols. The frequencies are 100, okay, 2, 2, which means this is sent 100 times a second, B is sent 2 times a second, and C 2 times a second. These are the frequencies at which, average frequencies at which they are sent through. Okay. Now we would like a code. These are the frequencies. We would like a code. Well, here is a good code. A is 0. Okay. This is 1 0, and this is 1 1. Okay, so let's look at this code for A, B, and C. Well, it stands to reason that I would like to use small number of bits for A because it's sent many times. right? So I would like to send a smaller number of bits across. So this has 1 bit, then I have 2 bits for B and 2 bits for C. Okay, so then it sort of I've used lesser number of bits which are transmitted across from left to right. Now this code has another property. Okay, so if I look at a string of zeros and ones going across, okay, decoding is easy. Well, the reason is this: supposing the first symbol is 0, I know it's an A for sure, right? If I hit a 1, if the first symbol is 1, I just look at the next symbol. It's either 0 or 1, and depending on whether it's 0 or 1, I know it is B or C. Okay, so let's do an example here. So I have A, B, and C, 0, 1, 0, and 1, 1. Let's take a binary string. Let's say 1, 1, 0, 0, 1, 0, 0, 0, 1, 0, 1. So how do I decode it? So I'm getting the symbols from left to right. I get 1, I check, I know it has to be either a B or a C. Okay, so this gives me C. I get as 0, this has to be an A, this has to be an A. Okay, 1, 0 means a B, 0 is an A, 0 is an A, 1, 0 is a B. Okay, 1, well, there has to be something else here, let's say 1, 1, and that gives you C. Okay, I can just look at the symbols as they arrive, the bits as they arrive, and decode. Okay, decoding is very easy. These codes which actually have this actually has a property which I'll tell you, which is that none of these is a prefix of another. Okay, 0 is not a prefix of any of these, and these two are certainly not prefixes of each other. So such codes are called prefix free codes. So prefix free codes. Okay, so CI, so if I have code C1, C2 up to Cn, CI is not a prefix of Cj for any ij. Okay, then it's called a prefix free code, and these you can see are easy to decode. Okay, I just keep looking at the symbols, and as soon as I get a code word, I am done. Okay, I know what the word is, so I write the word, I remove these, and I keep scanning. So we would like to construct prefix free codes. So that's an objective. Okay, given these symbols, I would like to construct prefix free codes, and given the frequencies, with each frequency there will be with each alphabet there is a frequency. I would like prefix free codes which minimize the average length of the message which is sent, which means the length of a message, I will think of the length as frequency times the length of the code word. Right? The code has some length L, so the frequency times length is the average length, and the sum over all elements I would like to minimize. Okay, so before I state this formally, let's observe that prefix free codes have a close connection to binary trees. Okay, so for instance, this code ABC, I can represent it this way: 0, 1, 0, 1, okay, A, B, C. Okay, so how do I? So basically, I want to show that given any prefix free code, there is a binary tree, and given any binary tree like this, I can get a prefix free code. Okay, so what is the secret of this transformation? Well, take any binary tree. Okay, the crucial things are code words at leaves. Okay, the leaves are where you get the code word. Okay, left branch is 0, and the right branch is 1. Okay, so when I take the left branch, I think of it as 0, the right branch I think of it as 1. And when you reach a leaf, you have traversed a binary string. Now that will be the code word associated with that with that symbol. Okay, so for instance, if I go left, left, right, left, and there is a code word there, it will be 0, 0, 1, 0. Okay, so given a binary tree with these code words at leaves, with these words at leaves, then I can assign a code word to each of these symbols. Okay, so maybe I should say symbols. Okay, given a binary tree with symbols at leaves, I can assign a code word to each symbol, right, using this 0, 1 business. You can check that this is prefix free. Okay, so why is this so? Because take any node in the tree. Okay, so this has some binary string associated with it, which is you followed the path from the root to leaf. Okay, and if you go right, you have a 1. If you go left, you have a 0. So there is a binary string associated, right? Now, what are the prefixes of this binary string? The prefixes are exactly those strings which you get at nodes which are in the path from the root to this node, right? If I only take leaves of a binary tree, no leaf is a prefix of another leaf. Okay, no leaf sits on a path from another leaf to a root, right? That's just not on. So the codes that you get this way are prefix free, and given any prefix free code, you can construct a binary tree. Okay, just in a simple fashion, you just go 0, 1, 0, 1 at each stage. Okay, and you follow this 0, 1 pattern, and when you hit a pattern which you want, okay, just remove everything below it, and that will be a leaf, and the word associated there with that will be the code word, the symbol which is associated with that code word. Okay. Right. So these are prefix free codes. What we want is you want to construct prefix free codes. Okay, before this, okay, let me just take a new sort of paper and write this entire problem properly. So the input is frequencies f1 and so on up to fn. Okay, what is the output that we desire? We desire a prefix free code, or in other words, a binary tree. Okay, and we would like to minimize the following function: sigma hi fi. Okay, I equals 1 to n. Okay, the frequencies come from there. Well, things with large frequencies must have short codes, which means they should be close to the root of this tree. Okay, so hi in fact is the height of symbol I in the binary tree. Okay, so the input are frequencies f1 through f1, fn. I would like to output a binary tree, and with each leaf I associate one of these words. Okay, either 1, 2, 3 up to n. Okay, one of these symbols, and I would like to minimize hi fi, the sum hi fi, where hi is the height of the symbol I in the binary tree. Fi is the frequency of symbol I, right? So this is what I want. Okay, now so how do I go about doing this? Okay, so given the binary tree, supposing that I give you a binary tree with n leaves. Okay, now can you assign these words to these leaves? Well, to minimize this function? Well, the answer is it's easy, right? So given a tree, since I want to minimize hi fi, I put items with the largest frequency as close to the root. So basically I take these leaves, I sort them in decreasing order of height, okay, or let's say in increasing order of height. I take frequencies, I sort them in decreasing order of frequencies, and I just pair them up. So if the tree is given, okay, then this is easy, right? The heaviest the items with the most frequencies must sit close to the root, and those whose frequencies are the least will sit furthest away from the root in this tree. The question is, what should the tree look like? There are many binary trees with n leaves. Okay, it's a good exercise to see how many. Okay, there are a large number of binary trees with n leaves. Which of these trees do we pick? Once we pick a tree, we are done. We know how to sort of fit these symbols into the leaves. Okay, so how do we pick these trees? Well, we would like to do some kind of exchange trick right here. Okay, even here, what would the exchange trick really mean? You know, you want to come up with a binary tree and you have these items which are sort of these symbols which are sitting. What does it mean to pick? What does the exchange trick mean? So what we would like to do is construct the correct tree. Okay, that's what we want to do. And so what does it mean to do an exchange trick? So supposing you have some tree. Okay, supposing you have some tree. You know that at the bottom of the tree, which means the node with the longest height, you have the two items with the largest frequency. The item with the largest frequency will sit there, right? So this much we know. So so we really know some part of the tree, which is if this is a tree, okay, this is a binary tree. Now at the bottommost point, somewhere here is the bottommost point, say, okay, I have ones with the largest frequencies. Okay, the two items with the largest frequencies will sit at the bottom of this tree. Okay, the other leaves are somewhere there. Okay, somewhere here maybe. Okay, this much I know. So I know part of the tree, right? I know part of this tree. What about the rest of the tree? Can I sort of somehow compute the tree part by part? Well, okay, so that's one thing. What would an exchange trick look like here? I mean, what do I exchange here? What do I exchange? Items. But if I exchange items, remember the tree remains the same, right? If I exchange items, the tree remains the same. So the exchange trick that we would like to try is exchange subtrees. Okay, so given a tree, I pick two subtrees and I exchange them and I see what happens. So this is the calculation we would like to do. And once we do this calculation, we would like to see what really happens, okay, to the average height. And from this, hopefully, we'll get a clue as to how to construct this tree.